All right, so we have this. Now that's pretty much all we need from the mass balance equation. Let us go ahead and see what this gives us for the momentum balance equation. Okay, so let's now turn to momentum balance. Okay, and let's rewrite it. It's rho partial of v with respect to time. We already know that first term is going to drop out because we have the fundamental assumption of steady flow. Okay. Now, we had written it out as divergence of P isotropic tensor plus 2 mu d. Okay. Body force we dropped out. Okay, so this is what we have, and then let's also remind ourselves that this term is gone. Okay, to make things easier now, I am going to sort of do what we did for the mass balance condition, the mass balance equation. I'm going to go to coordinate notation. Okay, here. All right. Using coordinate notation, this becomes rho vi comma j vj equals p delta ij plus 2 mu times 1/2 vi comma j plus vj comma I. All of this comma j. All right, and you note that what we have here is simply the spatial gradient of the spatial velocity plus the transpose of that term. Right? All of this indices I, j. Okay, that's what we have there. Okay, now let's look at this term by term. Let's first consider what we have in here. Okay? All right, we don't need to carry the rho along here. We can just look at what we have in those parentheses. And what this is vi comma j vj. Now, this term as well as what we have up here holds for I equals 1, 2, 3. Okay? And this also holds for I equals 1, 2, 3. But note that V1 and V2 are each equal to 0. And what that implies then is that we need to consider just V3 comma j Vj, okay, of the terms on the left hand side. Okay, so this is the only survivor, right? Okay, all right. So, but even this can be further simplified, right? Because now we have this contraction over j, and we already know that V1 and V2 are equal to 0. Okay, so what this implies then is that we have V3 comma 1 V1 plus V3 comma 2 V2 plus V3 comma 3 V3. Now, for different reasons, each of these terms is 0. V1 is 0, V2 is 0 because of that assumption that we made leading us to a semi-inverse method. And we've already demonstrated that V3, 3 equals 0. Okay? So what we've shown is that the entire convective velocity drops out. Okay? And therefore, our momentum balance is just divergence of the stress equals 0, right? And for the stress, we already have this relation. Okay? Let's go back to coordinate notation. We'd already written out this left-hand side now, what has now become the left-hand side. We'd already written it out in coordinate notation. Okay, so in coordinate notation, we have P delta ij plus 2 mu times 1/2 V I comma j plus V j comma I the whole comma j equals 0. Okay, and this holds for I equals 1, 2, 3. Okay, now we take the derivative with respect to xj here of p. Okay, that gives us a gradient of p, but then the delta ij does its job, right? So this basically becomes p comma I, right, plus the 2 mu and the half, sorry, the 2 and a half go away, of course. We have mu V I comma jj plus V j comma ij. Okay, again for I equals 1, 2, 3. All right. Let us now look at what happens with each of these, with this relation for each of the directions. Okay, and of course this is equal to 0. Okay, let's look at what happens for I equals 1, 2, 3. So for I equals 1, we have p comma 1 plus mu times v1 comma jj plus vj comma 1j equals 0. Okay, we already know that v1 equals 0, therefore this term vanishes. Okay, let us look now at what happens with this term. Okay, that is v1 comma 1, 1 plus v2 comma 1, 2 plus v3 comma 1, 3. Everything drops out, right? This drops out because v1 equals 0, that drops out because v2 equals 0. And here we see that v3 comma 1, 3 is basically the same as v3 comma 3, 1. Okay, but that is just v3 comma 3, the whole thing differentiated with respect to x1. All right, so this thing also equals 0. Okay, now exactly the same thing happens for I equals 2 as well. Okay? Okay? Again, this basically comes about from the fact that V1 and V2 are equal to 0. And we have V3 comma 3 equals 0 from the divergence condition. Right? So, what this implies then is since all of this on the right hand side drops out, right, all of this goes out, goes to 0, right, this implies that P comma 1 equals 0, P comma 2 equals 0. Okay? So the pressure is a function of x3 alone. All right? So from here we see that P equals P function of x3 alone. All right? Okay, so now let's go to I equals 3 and see what happens. Okay, for I equals 3 we have P comma 3 plus mu V3 comma JJ plus Vj comma 3j equals 0. Okay, implying that P comma 3 plus mu. Okay, let me expand everything out. The first term is V3 comma 1 1 plus V3 comma 2 2 plus V3 comma 3 3. Okay, and the second term, so all of these come from here. Okay, and the second term is V1 comma 3 1 plus V2 comma 3 2 plus V3 comma 3 3, and these terms arise from there. Okay, close parentheses equal to 0. Now again we can play out, we can invoke all the conditions we've derived. This thing drops out because it's V3 comma 3 3, but then we already know V3 comma 3 equals 0, right? Here we have V1 equals 0 from assumption, V2 equals 0 from assumption, again V3 comma 3 3 drops out. Okay, so truly the only equation we have left to solve is this one. Partial of P with respect to x3 equals mu V3 comma 1 1 plus V3 comma 2 2. But you recall that we'd set V3 equals to chi. Okay, on a previous slide, let me just go back there, we made the observation, I think it's 2 slides back. Right, here we are. We made that observation. Okay, what that implies is that out here, this is the only term that survives. Okay, and this is chi comma 1 1 plus chi comma 2 2. All right, now that we will write as chi comma, well, let me write it as exactly that, chi comma 1 1 plus chi comma 2 2. All right. Oh wait, it's not equal to this. It is that plus this equals 0. Okay, that's really the only equation we need to solve. Okay, we'll stop here and come back and actually solve these equations.